I'll get into it. Okay, so just 2 seconds on what universal market access, or UMA, or UMA, we say UMA, what it is and what we're trying to do. So we look at it as a decentralized financial contracts platform, really trying to build infrastructure to let people like you guys build financial products on Ethereum. The mission really is universal market access. So this really cool idea that, hey, we could actually create financial products that are actually globally accessible and not tied to your local like fiat government jurisdiction. And also guys, like interrupt me here, keep it interactive. There's really 2 parts to what we're doing. They're what we're calling self-enforcing contract design patterns. Mouthful, but what we really mean on the contract design patterns, yeah, sit down guys. On the contract design patterns, these are going to be contract types or contract templates that let us create useful financial products on blockchains. Examples are like what we're promoting for our Bounty synthetic asset tokenization. So let's create a token that tracks some synthetic asset in the real world. These could also be swaps and derivatives or like a decentralized BitNex or all kinds of other things. And then the second part of that is this oracle concept, this oracle that's going to power and provide real-world data onto the blockchain that drives those financial contracts. So these 2 concepts we think interact. These are both what we're doing. The financial contract templates are totally free, totally accessible. The oracle is our solution to powering how we resolve disputes in these contracts. So what we want to talk about is this idea of adding economic incentives to an oracle, economic guarantees. So why do economic guarantees matter for oracles? So it's a useful analogy, and again, guys, so I'm keeping this like pretty theoretical, so if you're all like sleep deprived, some of this might be like, but ask questions. A useful analogy here is to think about contracts in the fiat world. So stating the obvious, legal contracts are really useful. They let us build our modern financial system and all these types of financial contracts. They depend on counterparties believing in the contract and the reference data cannot be manipulated. So here we've got just a theoretical example of Alice and Bob. They write a financial contract for $1 million, and it depends on some price of some external reference. They're both happy to do this under the state of Massachusetts law because they believe, mostly, that the court system in the state of Massachusetts can't be corrupted. And there's laws in the fiat world, super useful, this concept of laws against fraud and manipulation that mean if Bob here tried to go and bribe the data source for this contract, he's going to go to jail. And you could literally like think about that economically as Bob having a huge economic cost to attempting to bribe the cost of this one. So he goes to jail. The problem, or really the opportunity, is in the blockchain world there is no concept of fraud. In this pseudo-anonymous, permissionless blockchain system like Ethereum, there's no laws against fraud or bribery. You can think of that actually as like a feature, not a bug. But it means that there's nothing to prevent Bob from corrupting an oracle system or a data reference of any sort. And so what that means is Bob can totally go ahead and bribe or corrupt any oracle out there. And when you think about this, this scales to be a really big problem. So we had this $1 million theoretical contract that Alice and Bob entered into, where Bob could steal half of it, theoretically. He could steal 500 grand if he were to corrupt this oracle system. But now scale that up, and Bob is pseudo-anonymous, you don't know who he is, and he writes contracts with Alice, Charlie, David, Fred, whatever, right? And now all of a sudden he can steal $2.5 million by corrupting this external price reference. And of course this scales to unlimited size. So Bob can theoretically have a massive incentive for corrupting his oracle system. So our point here of all this is that in a permissionless blockchain like Ethereum, private economic incentives are the only tool we have to incentivize behavior. If we're not going to go back and like use our legal system, we're going to really live in this new world. And so that's why we argue that economic guarantees here matter. In order to be able to trust that a smart contract that relies on off-chain inputs is going to do what it says it's going to do, we need to somehow prove that there is no economic incentive to corrupt the oracle or the price reference that this contract depends on. You guys with me so far? So get through this. This talks about Chainlink. Chainlink is great for a second. Like I'm just talking about the different types of Oracle systems here. There's other systems that are really useful for providing constant API, programmatic API access. What we're talking about is a little bit different. We're talking about something that is like more asynchronous, more expensive, but can really guarantee that the price source is not corrupted. And again, I'm going to go through some of these slides because there's a lot of them. So, okay, how do we build? What did I say? How do we build an Oracle with economic guarantees? So we define this concept of an honest Oracle. And there's two sort of sub-concepts here. We start with this idea that any Oracle on a blockchain is corruptible. Because our only tool is private economic incentives to incentivize behavior, it means that there is always some amount of money that you can pay somebody on some blockchain system or off-chain, price source or whatever, to corrupt it. And so we define then that the lowest cost at which you can corrupt the system, we define that as our cost of corruption. Separately, if you were to corrupt this Oracle system, there's all these contracts and all this value theoretically linked to it. What is the maximum profit? What is the configuration of the universe in which you could steal the most money? We define that as our profit of corruption. And then putting this together, we have our kind of definition of what an honest Oracle looks like. An honest Oracle is one where you can prove that the cost of corrupting this Oracle system is always greater than the profit you could make if you were to corrupt it. Does that make sense?
Yeah.
Ish? Yeah.
I mean, how would you like defend against like an irrational person?
You don't. So this does defend like that there's rational economic actors. And actually get really nerdy for a second. You can make an argument that say Jamie Dimon at JP Morgan doesn't like this future finance world, and so he spends $50 million to go and like blow this thing up, right? And that actually might be rational for him as like a one-time attack. But this is actually, Albert mentioned this in the Prisoner's Dilemma. If you turn it into an iterative game, it doesn't make sense anymore. Because this is just going to pop back up, and Jamie Dimon can't pay $50 million every time to shut it down. So ultimately, rational economic incentives, you can make an argument, will win out in the end as this thing gets big enough. But that's like tangential. Okay. Yeah. Anything else, guys? So, okay, just to explain this concept with our little diagram here. So Alice and Bob have their $1 million contract. The profit from corruption is how much money you could steal from this contract if you could control the price input. In this example, Bob could steal half the contract, but that's not his, 500 grand. Alice could steal 500 grand, so our profit from corruption is this 500 grand number. Our cost of corruption is whatever it would cost Bob to go and bribe the external price reference to corrupt this system. Okay. So then, how do we go about actually building this Oracle with economic guarantees? It is a three-step process. Create a system to measure this cost of corruption, create a system to measure the profit from corruption, and then design a mechanism to keep these two quantities, to keep this inequality in check, and prove it all works. So that's what we're going to try to do. I'm keeping this high level, got lots of white paper and other resources and get a lot deeper on this, but high level how we do these three things. So we measure our cost of corruption with tradable voting rights. So here we have a token where token holders have a voting right. Their voting power is weighted by the number of tokens they have. And we use a Schelling point style system where voters vote on price requests or price disputes here. And they're paid a reward for voting correctly, voting with the majority. They're charged a penalty for not. The game theory behind this is that it's like the 51% attack on proof of work networks. As long as there's an honest majority, the system will resolve correctly. Which allows us then to measure our cost of corruption. Our cost of corruption is whatever it costs to buy 51% of the voting power. Yeah.
Or borrow 51% of the voting power.
Not exactly, right? So this gets really interesting here too, where if you could borrow 51% of the voting power, like you win for sure. But then you've got to think through what the economic incentives of the lenders of the voting rights are. If you're lending your voting rights here, it's not like you're lending something really valuable. So you really should be very, very fearful of lending your voting rights to the wrong person, because if you lend them really cheap, then someone can corrupt this thing, and this voting right that you had that was valuable goes to zero. So, but it's like a really interesting line of thinking about like, okay, what happens if people do lend their voting rights? What are the economic incentives there? That's a very good question. Yeah.
So what does it mean to vote correctly in this instance?
Majority rules, which is also a really interesting question, right? It's like you can get like really philosophical, like what is the truth here? The truth is whatever the majority says. Yeah, you get really philosophical on it. But it's an interesting question when you actually think through like some kind of real world examples that are kind of fun to think about. You guys remember the Coinbase flash crash, right? Where, I forget whether it was ETH or Bitcoin actually, but the price dropped like 50%. These types of flash crashes happen in like other traditional financial markets too. Do you consider that a good price or not? Like, is that price considered accurate or not? And the answer is it depends, right? So like the CME, when this happens with traditional futures contracts, they decide whether they want to honor those prices and consider that real or not real. In this case, if you think about it from this context, whether that happens or not, whether that's considered a good price or not, would be up to the majority. What do people think? Okay, I'm probably going to take too long. Sorry. So, second part, measuring our profit from corruption. So when we go back to the individual contract, it's easy on an individual contract to figure out what the profit from corruption is. How much money could get stolen out of that contract if an attacker were to control this price feed. So our system-wide profit from corruption number simply sums all of the contracts using the system, and it's like a worst case analysis. In the worst case, how much money could be drained from the system by an attacker if they were on one side of all these contracts. In order for us to measure that, contracts have to register with the Oracle, or with what we're calling our DVM, or data verification mechanism, to allow us to calculate this system-wide PFC number. Yep.
Is it possible to have parasitic interest on them?
It is. We have a super interesting parasitic usage solution, which involves like some zero knowledge stuff. I'm not the best guy to speak on it. It's in our white paper at a high level, and it's something actually that we're going to be talking about more. It's really damn cool, but we think we have a theoretical solution on how to get around that. In the early days, we're not going to worry about it too much. Yeah?
What's parasitic usage?
Sorry. This whole concept of measuring our profit from corruption is premised on the fact that we know what's using the system. If we don't know what's using the system, then we can't measure it, and the economics of this break. And you can then make an argument, well wait, if there is a cost for using the system, but then and people don't have to tell us they're using it, well then there's an incentive to parasitically use the system. Augur kind of introduced the term, at least they're the first person I know that's used it. Augur introduced the term of parasitic usage, where if the parasites get too big, they kill the host. And I think it's a good analogy. We again do have a solution for how we can like absolutely limit who can use the system. And yeah, it's a fun thing to talk about. But we'll leave it. That's good for now. Okay. So we got part one done. We can measure our cost of corruption. We got part two. We can measure our profit of corruption, barring this parasitic question, right? Part three, how do we enforce this inequality where we make sure that the cost of corrupting the system is greater than what you could steal? And we do this with what we're calling a variable fee policy or variable tax policy, where if and when the cost of corrupting the system approaches the floor, so basically as that inequality gets threatened, we levy a tax on the users of our system. So these are on the contracts using the system. We charge them a fee, and we use that fee to purchase the voting rights in the open market to support the market cap of the cost of corruption. And because we do this programmatically on the blockchain, it's completely credible, and it's going to happen. So we have this very cool circular effect, right, where actually users of the system, third-party speculators, if they see this inequality getting threatened, they know that this market force is going to come and start buying tokens. So arguably, you can think of third-party speculators having a free option as the market price approaches this floor. That's probably the funkiest part. We'll go in a bit more detail on it, but that's like the high level of how we enforce this inequality. Yeah.
Would you ever mint tokens if one is much less than the other?
No, I don't think so. So there's this, going off, thinking about this from a business perspective. You think about what a business tries to do is they try to like maximize profitability, right? They want to create the most money possible, and in that case, they might issue shares or something. If like their share price is really high, they go try to like raise more money or something like that, right? In our case, what's really interesting is we are not trying to maximize profit. We are only trying to ensure this inequality stays in check. So it's like we want to make sure that we're going to charge enough, we're going to charge enough fees to make sure this inequality stays in check, but no more. And actually, it's kind of really interesting. This is the fun shit about this like Ethereum, blockchain, crypto stuff. Like it's a fun and interesting, weird business model to think about, where hey, you're trying to make enough money just to guarantee the security of the system, but you're not trying to extract rent past that. All right, there's some math here. Do you guys want to go into math?
No.
Yeah? All right. So to measure the cost of corruption, an attacker must control half of all participating tokens. So what I mean by participating tokens is if there's a lot of voting rights out there that aren't voting, right? They don't actually secure the system. So we have this ADA parameter that's just the percentage of non-participating tokens. So our Y value here is the number of token rights that half of the participating tokens supply that an attacker would need to control to corrupt the system. Then our cost of corruption is then the price at which it costs to buy these tokens. We call that our cost of corruption. This is actually pretty simple. This is just what I said in words. Measuring our profit from corruption is simply the summation of all individual contracts, profit from corruption numbers. And that gives us our system-wide PFC number. Then we rearrange and solve for this inequality. So we put those two things together and we solve for the price of the token that needs to be maintained to keep the system secure under this cost of corruption, profit from corruption framework. And basically what it's saying is we need twice the profit of corruption divided by the participating token supply. And if you just to put some real world numbers around this, if we assume that the contracts using the system are symmetric, so let's say we have, going back to the Bob Alice example, we have that $1 million contract. Let's say we have $100 million of contracts in the system, total margin in the system. At any given point in time, the profit of corruption would be $50 million, half the value of the system. Which means we need the cost of half of the voting rights to be more than $50 million. Multiply everything by 2, we need the market cap of these voting rights to be greater than the total margin in our system. Okay. This is a short presentation, so I'm not going to go like we're supposed to be. How do we do, and then I add this last thing. We create like a buffer, so we call it a safe price as a buffer above this floor price. We call it our safe price. Okay, so then how do we maintain this safe target? This is just through this programmatic buyback. So every period, every voting period, we calculate what our target price is by observing the system-wide profit of corruption. We look at what the current price of the market cap is. If the system is below where it should be, we levy a tax. We calculate the fee we need to keep the system secure. We levy a tax and we conduct a buyback. And we do this repeatedly. This is like central bank containment currency peg. We do this repeatedly and programmatically. More math. But what's really cool about this, so what this actually looks like is sort of a perverted discounted cash flow model for traditional like companies, where the value of a company's stock at any given point is the market's expectation of all future dividends. In this model, the value of our voting token is the market's expectation of all future buybacks, of all future taxes. And what's really cool about that is that in the early days of the system, when there is growth expected in use of the oracle, the market will put the price based on that expectation above the floor, above where it should be. Which means that in the early days of the system, it's costless to use the oracle system. Or as long as there's an expectation of growth, it's costless to use this oracle. That we think is kind of cool and kind of wild, where we're actually able to use economic incentive. We're actually able to use the expectation of future buybacks to subsidize the cost of using the oracle system in early days. All right. So where are we in implementation? We have a white paper that's out. This whole presentation, guys, is linked in the Discord channel and elsewhere. And it's all on our GitHub. There's a tweet storm that you guys can check out that summarizes some of these concepts, kind of goes through what I've talked about here. We would love feedback on this white paper and feedback on the mechanism and like critiques on this whole way of thinking about the world. Love that. We also have our code out, and it's on testnet. It's all up, it's live, like we've actually built this thing. It is V1, right? It doesn't do doesn't have all of our feature set, but this is more than theoretical. And again, we'd love any feedback or critique on it. And then yeah, these are the four of us that are here. Come find us and talk to us about this. Remember, we're here actually doing the more concrete bit. We've got this synthetic token thing, right, where you can go and use our system, our infrastructure, to build a synthetic token to track real-world assets. This is an example of a use case, a DeFi use case, that then plugs into our oracle on the back end. So this whole talk is about the theoretical oracle underpinning this thing. And that's it. And actually, I think I sort of followed time, mostly. So yeah.
How are you making money off of this thing? I mean, like, how are you going to support your business?
We, in true crypto form, we don't want to have a business. We just want to own some of the token supply. So the whole premise of this is that these voting tokens should be valuable if we can make this oracle be useful as this dispute resolution mechanism, this oracle of last resort that is truly decentralized. If we can make that a useful thing, these voting tokens will go up in value. And so we actually want to provide a lot of shit for free, a lot of shit that's just open contributions, specifically when it comes to financial contract infrastructure. So stuff that just needs some oracle. We want to provide that all for free, like our synthetic tokenization contracts and other things, purely out of the intention that these DeFi contracts, that DeFi will grow and will use our oracle, increasing the value of voting rights. Yeah.
So then would one path to profitability be to either set up a consortium or join one, or basically like amass of, let's say, like ISDA members, and then try to get them in on this voting token, and then try to like, in some weird post-Basel / whatever it's called, try to bring some of those OTC contracts like on chain, so that way and then through that, like, is that what you guys are thinking, or is that like a route, or?
Maybe. So to give everybody else some context, like ISDA stands for International Swaps and Derivatives Association. They are like the main association that actually writes the legal templates for institutional derivative traders. I think it's interesting, right? But we're just much more interested in the grassroots approach, where institutional derivatives work well, right? They work well enough. If you've got $100 million and you want to like trade shit, go for it, right? We're really much more interested in creating a system, or creating this DeFi thing, where if you think about what our name is, universal market access, we're much more interested in how we can create synthetic financial contracts or this global financial infrastructure and look at this as a grassroots thing. So token distribution, like we're not doing some like crazy token launch. We're going to do this very organically and to spread these tokens out to people that will vote. The one thing we care a lot about is voter participation. So we want these tokens to be spread far and wide and pretty organically and pretty grassroots-y. And frankly, I think it is a long, long way before institutional counterparties care about doing something quite this radical. Yeah.
Yeah, Hart, another question. So there's the, maybe it's in white paper, I didn't see, but like, so you outlined clearly the demand for the token, but under what conditions are you gonna sell this? How does it work? Do you have anything to sell the token? If it, to balance these, the costs and the profit? Are you selling back at any point in time?
Kind of like in equilibrium in the future, or
Yeah,
like in the near term, like what is token distribution?
So you're worried about the cost being less than the profit, right?
Mm-hmm.
So you buy, right, to make it more expensive,
Yep.
to corrupt the system. Does it work in the other way?
That's interesting. So we don't think it needs to, because in the other way, basically if the token value is trading way above where it needs to, that should be market expectations of like future usage, and the whole thing just means the system is more secure, right? Now what I care a little bit about is like rampant speculation or like that kind of shit. That's sort of bad, but I think we just use words and rhetoric to kind of temper people's expectations and keep them level-headed.
So there's always demand for the token, essentially.
Yeah, there's like this is like a fixed supply
Fixed
thing.
supply, but always a demand. Okay.
Yeah. Yeah, well,
Can you say a little bit more about how the fees are collected?
yeah, so there's a few different implementations or possible implementations that we've looked at. What we do right here is there's basically like a notice. It's almost like consider like a tax notice that gets issued by the Oracle if fees need to get collected. And because we have this registry, the way the interface for contracts using the Oracle is written, we want to be able to go in and collect those taxes on a close to real-time basis. But in all honesty, this isn't all like totally finalized or settled. So it's still sort of there's a few different possible implementations on how we pursue this. And frankly, we'd love feedback.